How would you go about calculating the sum of 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 on and on to infinity? Well, the simplest way is to find the partial sums, that is, the sums of the first 2, 3, 4, 5 terms, and then graphing them and seeing where they converge. In fact, we can ask Desmos to do it for us, and it's pretty evident that the sum approaches 2. If you want to be a bit fancy, you can calculate the partial sums, find the formula for the nth partial sum, and then find the limit of that as n approaches infinity. In our example, we have 1, 3/2, 7/4, 15/8, 31/16, and so on. You might notice that the denominator is always a power of 2, and the numerator is always one less than the next power of 2. We can write the nth term as 2 to the n plus 1 all over 2 to the n. Now, what would be the limit of this as n approaches positive infinity? 2 to the n plus 1 equals 2 to the n times 2. We can split the fraction into 2 now. 1 over 2 to the n will approach 0, since 2 to the n will approach infinity, and we can simplify the first fraction to simply 2. Therefore, our limit is 2. However, this method is much harder to apply with other sums. For example, 1 plus 1/3 plus 1/9 plus 1/27. You might notice that the partial sums, 1 4/3, 13/9, 40/27, have sums in their numerators, so a simple equation won't work. In fact, there is a third and way easier method which you can apply to many infinite sums, products, fractions. Basically, you just have to exploit the fact that they are infinite, and exploit the wonderfulness of algebra. Here's how you can solve the second problem. Say that s equals the aforementioned sum. Now subtract 1 from both sides, and then multiply both sides by 3. You'll notice that the right side is exactly equal to the sum, s, above. Remember that since it's infinite, it doesn't matter how many terms you take away, the rest will still be infinite. Now just solve the remaining equation. You'll find that s equals 3 over 2, and you can verify this with Desmos. You can also use this trick for infinite fractions. If you write something plus 1 plus 1 over 1 plus 1 over 1 plus 1 over, and so on, you'll notice that the fraction contains itself, so you can say that f equals 1 plus 1 over f. Now if we multiply both sides by f, subtract f and 1, we get f squared minus f minus 1 equals 0. Using the quadratic formula, we can conclude that f equals 1 plus minus the square root of 5 all over 2, which is also called the golden ratio, written with the Greek letter phi. If we look at the first example, we can generalize that sum if we notice that it was the sum of the reciprocals of increasing powers of 2. In fact, there's a special notation mathematicians use to write such sums, and it's called sigma notation because it uses the capital Greek letter sigma. By the way, did you know that sigma has 3 versions? One is uppercase, one is lowercase inside a word, and one is lowercase at the end of a word. To use sigma notation, we write some letter, usually n or I, at the bottom, and we write what value it begins at. At the top, we write the final value that it reaches. Then we write some arithmetic expression involving this letter. In our case, it's 1 over 2 to the n for n from 0 to infinity. From our previous algebra, we can conclude that it's equal to 2. But the magic of algebra is that you can generalize stuff. So let's do that here. Instead of just the sum of 1 over 2 to the n, we can try to find the sum of any 1 over a to the n for n from 0 to infinity. We can use the same method as before. Subtract 1 from both sides, multiply by a, rewrite s, add a and subtract s, factorize, and divide by a minus 1. This tells us that the sum is equal to a over a minus 1, which checks out with our result of 2. Now let's try some different values of a. We can graph y equals a and the corresponding sum on the same graph and see how it changes. For a equals 1, we get 1 over 0, which is undefined, as we concluded in the previous video. If we consider this example, it's actually 1 plus 1 plus 1 plus 1, which approaches infinity. It checks out. However, if we look at numbers below 1, things start to break. For a equals 0, we get 0 over minus 1, which equals 0. However, if we actually consider the sum, it's 1 over 0 to the 0th, plus 1 over 0 to the 1st, plus 1 over 0 squared. All of these are undefined, so we can't actually calculate the sum. For a equals minus 1, we get minus 1 over minus 2, which equals 1/2. It looks like it's correct since the sum fluctuates between 0 and 1, but it's not. To demonstrate why, I'll prove to you that the sum 1 plus 2 plus 3 plus 4 and so on equals minus 1/12. So if we say that 1 plus 1 minus 1 plus 1 minus 1 equals 1/2, we can write down a second sum, 1 minus 2 plus 3 minus 4 plus 5. Let's call it S2. If we add it to itself, we get 2S2, but we can rearrange it in a particular way so that once we perform the addition, it will be equal to S1. So S2 equals 1/2 of S1, which equals 1/4. Now I'll subtract S2 from the original sum we're trying to find. Let's do this step by step. 1 minus 1 equals 0. 2 minus minus 2 is 2 plus 2, which is 4. 3 minus 3 is 0. 4 minus minus 4 is 8. 5 minus 5 is 0. 6 minus minus 6 is 12. You can see the pattern. We can factor out a 4, and then what's inside the bracket is the original sum, 1 plus 2 plus 3 plus 4. So we know that S minus S2 equals 4S. So 3S equals minus S2. S equals minus S2 over 3, which is 1/4 divided by 3, which is minus 1/12. Now we all know that's not true. It goes up and up to infinity. So where's the mistake? Well, I kind of spoiled it. The mistake is in the first statement. But there's also one in the final statement. You see, we cannot say that a sum is equal to something if it never converges. And neither can we perform calculations with such sums. They are said to be divergent, and they have an undefined value. It's easy for us to tell when a sum approaches infinity. The partial sums simply get bigger and bigger, or smaller and smaller. But with the case of 1 plus 1 minus 1 plus 1, it's actually also divergent, because it doesn't approach anything, it just hovers around two values. So, that's how you can, and why you sometimes can't, calculate infinite sums.